Hi everyone and welcome to this episode of Kipet Labs. In today's video we're going to go through how to construct and get meaning from nuclear equations. So we're going to introduce ourselves or get familiar with what we mean by a nuclear equation and distinct from the typical chemical equation that you're used to. We're going to go through what we call nuclear notation, something that will seem a little bit familiar to a degree, so we're going to define it and then give you some examples of what it looks like. And also then go through some examples for some nuclear equations. Okay, so when we're talking about a nuclear equation, we're looking at a chemical equation or an expression that shows the changes that occur in the nucleus. So particularly when we're thinking about radioactive decay or radioactive processes, like the formation of new radioisotopes or the breakdown of existing ones. Okay, so that might be in thinking about alpha decay, we might be thinking about beta decay, looking at neutron capture and also or what we would call kind of bombardment with neutrons, which we'll look at when we look at production of radioisotopes, electron capture, and then also nuclear fission, where this idea of a nucleus that kind of splits into two different nuclei. Excuse my scribbles, trying something a bit different here. Okay, so all of the nuclear equations help us to understand these processes. Now, the reason that we care about them, or that we want to use this, is that the electrons around the atom are not, unlike in most chemical equations, the electrons are not involved in these processes, except kind of circumstantially. So it's actually the nature of the nucleus, which is normally ignored, that is the key thing here. So we need to express them a little bit differently. So to that end, that we're going to use something we call nuclear notation. So a symbolic way to represent the structure of a nucleus. Okay, so we've done this sort of thing before, you just didn't necessarily call it nuclear notation. So it looks like this. Okay, so that we have the symbol for the element, so whatever it is that comes from the periodic table. And then we've got two numbers written on the left, in the top left-hand corner and the bottom left-hand corner. Okay, so the bottom left-hand corner is our atomic number, Z. Okay, so the number of protons in the nucleus. So uranium is 92, sodium is 11, hydrogen is 1, lithium is 3. And then we write the mass number in the top left-hand corner. Okay, so remember the mass number is a whole number, the protons plus neutrons in the nucleus. Okay, so uranium might be 238. Sodium might be 23, calcium might be 40 or 48 or something like that. Okay, so the idea is that we will write the symbol and then these two numbers are written on the left. So then we will use nuclear notation when we write a nuclear equation because we want to keep track of what's happening with these numbers as we go. So to give you two quick examples. Okay, so let's look at the isotope carbon-14. Okay, so using our periodic table, and hopefully this is automatic by now, that carbon, we recognize that carbon's got the symbol for C, that it has an atomic number of 6, and that this particular isotope we're referring to has a mass number of 14. Now, not everyone will, but in this case, that's what we're referring to. So if we take these three pieces of information and we combine them together, we get this as our nuclear notation. C for carbon, 14 for the mass number, and 6 for its atomic number. If we have a look at uranium-238, one of the isotopes of radioactive isotopes of uranium, it's got the symbol of U, atomic number 92 from the periodic table, and we're identifying the mass number of 238. So we will write it like this. Okay, so still sticking with those two numbers on the left and the symbol on the right. So this is the way that we're going to be expressing it. So now if we have a look at a nuclear equation. Okay, so we've talked about this idea of alpha decay in the past, so where we're giving off essentially a helium nucleus. Okay, so when uranium-238 undergoes alpha decay, it turns into thorium-234. Okay, so what we show is we've got our uranium-238 expressed over here on the left, okay, in its form, and now we're showing that we've got thorium, and we've got our helium nucleus, which is our alpha particle. Okay, but we write it this way because it actually contains 2 protons and 2 neutrons. So what you might notice from here is that the mass number over on the left is equal to the sum of the mass numbers on the right. The atomic number on the left is equal to the sum of atomic numbers on the right. Okay, so 90 plus 2 equals 92, 234 plus 4 equals 238. So that those numbers must be equal because mass is conserved. Okay, now if we have a look at, say, carbon-14 undergoing beta decay into nitrogen-14, okay, so we've got carbon-14 over on the left, Okay, we're undergoing beta decay, so we're giving off an electron. So this is how we would write an electron, this beta particle, in nuclear notation, because we would say it's essentially got no mass. It does, but then the mass is so small that we can't round it up to 1. Okay, it's essentially 0 in these forms, but that we would give it an atomic number of -1 because it is, a single negative charge as opposed to the single positive charge on a proton. Okay, and so then that means that when we form nitrogen-14 that looks like this, that the same process applies, that our mass numbers, the sum of the mass numbers is equal, 14 plus 0, and our atomic numbers is also equal. So we go from 7 minus 1 is the same as 6. Okay, so both of these equations show these changing processes. Both have mass and atomic numbers the same on both sides, the sum, so to show that conservation of mass as we go through. Okay. So we introduced the phenomenon, or kind of what we observe as a nuclear equation, to talk about the changes that happen in the nucleus, not in the electrons. We introduced or reminded ourselves of nuclear notation, so how we would define it, and also the examples of how we'd write it, and then showing how we would employ nuclear notation in nuclear equations. Thanks very much for watching. Bye for now.